We're in AP Calculus Lesson 2.5, Part B. We're continuing to solidify this concept of the derivative as the slope of the tangent line, and looking at this in a variety of ways, analytically, graphically, and numerically. In this problem set here, for questions 10 through 15, we have a table of numerical values. So we're looking at this numerically, and looking at, before we even look at our specific questions, what is our table representing? Well, our table represents the derivative of a function for various values of x, and they tell us that here, h of x, and they tell us that the original function is a polynomial function, h. And there's certain things we can assume from a polynomial function. Think for a moment, what are some attributes of polynomial functions? One is that polynomial functions are continuous. They're continuous on their domains. Okay. We also know that polynomial functions are smooth. And we'll eventually learn that polynomial functions are differentiable at all points. It's a little bit of a gimme here. For now, differentiable. With this information, we can answer some questions about our table. Our first question asks, on what interval, which tells me I'm going to have some interval from one x value to another x value, is the function h, which is not specifically indicated on our table, increasing and decreasing. So we're going to start with increasing, and it asks me to give the reasons for my answers. I like to give my reasons first because that tells me what to look for. So h of x is increasing. How do I know where the function is increasing? Well, the function increases where the derivative is positive. On what x values, what range of x values is my derivative positive? Well, here's my derivative, and these values are positive. No other values are positive, and since this function is continuous and differentiable, and it tells me that the only zeros of the derivative are indicated, meaning that's the only place my derivative will change signs. That means that this derivative is positive all the way up to, but not including, h prime equals 0. So for my x values, I'm going to take at negative infinity. That's going to be continuous, continuing to go up this way, on the interval from negative infinity until which x value? Well, all the way up to, but not including, negative 2. Then we're also asked, on what intervals is the function decreasing, and give our reason. So h of x is decreasing on the interval. Well, first, how do I know? I know that it's decreasing. My function is decreasing where what? Well, where my derivative is negative. Function decreases where the derivative is negative. And looking at this chart, where is my derivative negative? Well, here's h prime of x, and it's negative for these values and for these values. And again, because this is a polynomial function and my only zeros are indicated, I know that this goes all the way up to 0, but doesn't quite touch it. And same thing here and here, and then continues off to infinity. So what is my first interval? What is my first interval in which my derivative is negative? Well, the end point will be x equals negative 2. Not at negative 2, because the derivative is 0 there. It's not decreasing. It's not a negative derivative there. But all the way up to, that's why I use my parentheses, x equals negative 2. And when does it stop being negative? Well, it stops being negative at x equals 7, because for that moment it becomes, the derivative is 0, and I have a relative minimum or maximum instead of an increase or decrease. Write the x value there. I do have another interval where it's negative, and that is starting at 7 again. And when does this interval end? Where does my derivative cease to be negative? Well, for all intents and purposes, to our knowledge, it just continues to be more and more negative. And so I would say all the way until x approaches positive infinity. And that's my interval. Question number 11 asks, at which x values does the graph of the function have a relative maximum? Justify our answer. So we're going to start with our justification. How do I know where the graph has a relative maximum? H of x has a relative maximum where? Well, a function has a relative maximum where the derivative equals 0, remember our horizontal tangent, and changes our maximum looks like this, so that's from positive slope to negative slope. Now, where does this happen on my chart? Well, here my derivative is positive, here it becomes 0, and here it changes to negative. And I don't change from positive to negative anywhere else. So this will be at the x value, x equals negative 2. Number 12 asks, at what x values does the graph of h have a relative minimum? Well, h of x has a relative minimum. How do I know where my function has a relative minimum? Well, where my derivative equals 0 and changes from, well, a relative minimum is going to have a negative slope and then change to a positive slope. So changes from negative to positive. There's my reason. Now, where does my derivative change from negative to positive here? This is positive, this is negative, then it changes from negative to negative. So do I have a relative minimum? No. Therefore, h of x has no relative minimum. It has no relative minimum. It's not enough for me to simply say, nope, no relative minimum. I still need to justify why there is no relative minimum. Well, because a relative minimum is where my derivative changes from negative to positive, and it didn't change from negative to positive anywhere. Number 12 asks, if h of 3 equals 2, so this is some preparatory information, what is the equation of the tangent line? That's what I'm solving for, what I'm finding, to the graph at x equals 3. And then I have a new question. So let's start with this one. What two pieces of information do I need in order to find the equation of the tangent line? I need the point of tangency and the slope of tangency. How do I find my point of tangency? It's actually in the question here, number 13. Where am I given what my point of tangency is? My point of tangency is 3, 2. Because I'm given that of h of 3, which would be written h of x equals some y value. So I'm saying that x equals 3, and when I take the function of 3, I get a y value of 2. And that's my point of tangency. How would I find my slope of tangency? What should I think when I think slope of the tangent line? My slope of tangency will be the derivative at x equals 3. I'm given a chart of derivatives. At x equals 3, my derivative equals negative 3. So I know that my slope of tangency is -3, and that is my m, or my slope. To find the equation of my tangent line, then I use the point-slope formula. Y minus y1 equals -3 x minus x1. Distribute and add 2 to each side. Gives me y equals -3x plus 11. Then the second part of my question asks me to find the equation of the normal line. Now, what's different between the equation of the normal line and the equation of the tangent line, or what is the relationship between those two? Well, whatever my equation of my tangent line is, my normal line is going to be perpendicular to my tangent line, which means that its slope will be the opposite reciprocal. My slope of normalcy, or m sub n, will be the opposite. This was negative, so this will be positive. Reciprocal. To find the equation of my normal line, then, I use the same point of tangency. That's now my point of normalcy, is 3, 2. Except now I have a slope of positive 1/3. Y minus 2 equals 1/3 x minus 3. I can distribute that. 1/3 x minus 1. And add 2 to each side. Y equals 1/3 x plus 1 is my equation of normalcy. Number 14 asks me to find the tangent line approximation. That means I'm going to use the equation of my tangent line. The equation of my tangent line, which is here. Y equals -3 x plus 11. And they ask us to use that to find h of 3.1. So I'm not being asked to actually find my function at 3.1 because I'm not given an equation for my function. I'm not given h of x equals some function anywhere. But I can approximate that by using the equation of my tangent line. So I'm just going to evaluate my tangent line at this 3.1 figure. -3 times 3.1 is -9.3, which will be 2.7. And that's my approximation. Finally, I'm asked to find two limits. The limit as x approaches -infinity of h, and the limit as x approaches positive infinity of h. Now, they're not asking us to find the limit as h prime of h prime. If I were finding of h prime, I could just look at my chart, read off to the left, and read my h prime. What I want to know is what's happening to my function as x approaches -infinity. So I need to think about this logically. If my derivative is positive, then the slope of my function is positive. My function's increasing, which means as I go to -infinity, my function is going down and it's approaching -infinity. How about as x approaches positive infinity? Well, here my derivative is negative. That means that I'm going to have a negative slope, and as I read that to the right, my function is approaching -infinity. So these ones really test our ability to think through the question, that we're really checking. It's not asking us to find the derivative, it's asking us to find the function based on the derivative. Our fourth page here asks us to work analytically, and we're told we have a polynomial function, which means continuous on its domain, and the information we're given is not the function, but is the derivative. We're given the derivative equals x times 2 minus x times x plus 3. And we want to use that to find this information. Our first question asks, on what intervals is the function increasing or decreasing, and justify those answers. So let's start with our justification. We know that f of x is increasing. F of x increases where what? How do I know where the function is increasing? Well, where the derivative of x is positive. Where my derivative is positive, my function is increasing, which is on the interval, and we'll find that out in a moment. So I know I need to find out where is my derivative positive. I can also tell where my function is decreasing. It's decreasing where what is true? Well, conversely, where my derivative is less than 0, which will be on the interval. And we'll find that now. So I need to find where my function is increasing, where my function is decreasing. In order to figure this out, I need to know where is my derivative positive, where is my derivative negative. So I'm going to use a sign chart and break this up into portions, different intervals. And to determine these intervals, to define these intervals, I need to know where are their endpoints. And the only place I can change from a positive derivative to a negative derivative, or a negative derivative to a positive derivative, is where my derivative equals 0. So I need to take my derivative function and set it equal to 0. In this case, my derivative, which equals x times 2 minus x times x plus 3, setting that equal to 0 allows me to use the 0 property. So x equals 0, 2 minus x equals 0, which is x equals 2, and x plus 3 equals 0, which is x equals negative 3. So these are my 3 zeros, and these are what I will plot on my sign chart from least to greatest, negative 3, 0, 2, which gives me intervals of negative infinity to negative 3. This interval will be negative 3 to 0. What will this interval be? 0 to 2. And this final interval? 2 to infinity. Now I have two approaches I can take to determining where's my derivative, on which of these intervals is my derivative positive, on which of these intervals is my derivative negative. And the one that we'll use most often is the polynomial curve sketching. I need two pieces of information for the polynomial curve sketch. The first is my multiplicities, and for each of these roots, each of these places where my derivative equals 0, I found each of these roots only once each, so they're a multiplicity of 1. The other piece of information I need is the end behavior. And when my polynomial is factored like this, I can find my end behavior by multiplying the x's and their signs together. X times negative x times x is negative x cubed. Now the end behavior of positive x cubed would rise to the right and fall to the left. Negative x cubed is going to vertically reflect that. It'll fall to the right and rise to the left. This means on my sign chart that my derivative function, that's what this is here, my derivative function, will rise to the left, meaning it will be positive, and fall to the right, meaning it will be negative on this interval. Then since my multiplicities are all odd, I'm going to cross and change from positive to negative here, and from negative to positive here, and then from positive back to negative, which matches my end behavior. If you're not as comfortable with the curve sketching approach, then you would choose test values, say negative 4, -1, 1, and 3, and check the derivative at each of those test values. So check my derivative at -4. It doesn't have to be an exact number, I just need to determine my sign. -4 here would be negative. 2 minus -4 would be positive. -4 plus 3 would be negative. Negative times a positive is negative. Negative times a negative is positive, which would make this positive, which matches up here. And you can do that for each of these values. It takes a lot more time, so we're going to use the curve sketching approach just for the virtue of saving time as we're solving these problems. With this, I can now tell where is my derivative positive from -infinity to -3, from 0 to 2. So that's my first interval, set of intervals. Intervals on -infinity to -3 and 0 to 2. And where is my function decreasing? Where my derivative is negative, which is on the intervals -3 to 0 and 2 to infinity. Number 17 asks, where does my function have a relative minimum? And justify your answer. So where does my function have a relative minimum? Minimums are where my derivative does what? It changes from negative to positive across a 0. So I can say that f of x has a relative minimum where f prime, my derivative of x, equals 0 and changes from negative to positive. And looking at my sign chart, I change from negative to positive across x equals 0. Do I change from negative to positive again? Nope. So just that one value at x equals 0. So I've determined at what value of x, at x equals 0, my function reaches a relative minimum, and I justify that based on the derivative equaling 0 and changing from negative to positive. Similarly, number 18 asks at what values of x does f of x reach a relative maximum? So again, I'm going to start with my justification. F of x has a relative maximum where the derivative, how do I know that it has a relative maximum? Where the derivative equals 0 and does what? Changes from maximum will look like this, which starts with a positive derivative, hits 0, and becomes a negative derivative to negative. Now, where does my derivative, according to my sign chart, change from positive to negative? Well, here I have a positive to negative that happens across x equals 3. That's the point where it changes. That's where the derivative equals 0, is at -3, and it changes from positive to negative. Does it change from positive to negative anywhere else? Yes, my derivative changes from positive to negative across x equals 2. Those are the two places it changes from positive to negative. Number 19, if f of 4 equals -1, what is the equation of the tangent line? This is what we're finding. Drawn to the graph at x equals 4. What two pieces of information do we need to find the equation of the tangent line? We need the point of tangency and the slope of tangency. What piece of information in number 19 gives me my point of tangency? Well, I get that information from this right here, which says that x equals 4 and y, my function, equals -1. So my point is 4, -1. How do I know where my slope of tangency is? What is my slope of tangency? When I think slope of the tangent line, I should think derivative at 4. That's going to be the derivative at 4. How was I given my information? Well, I was given the derivative analytically. My derivative equals 2 times 2 minus x times x plus 3. If f prime of x equals 2 times 2 minus x, x times 2 minus x times x plus 3, then the derivative of 4 equals 4 times 2 minus 4 times 4 plus 3. Which will be -56. Now that I have both pieces of information, I could find the equation of my tangent line, y minus y1 equals m, -56, times x minus x1. Y plus 1 equals -56, x plus 224. Y equals -56, x plus 223. I could also use this form right here once I simplify my x plus 1's. My last question asks me to approximate the value of 4.1, the function of 4.1. Now I don't have an equation for the function, but I can use a tangent line approximation, which means I use an equation of the tangent line. Since I'm working with 4.1 and I have a pretty big slope here, it would actually be easier to use this form of the equation now, because I'll be using 4.1 minus 4. Then I'm dealing with 0.1, and this is a lot easier to work with. So I'm going to use this tangent line approximation. Y plus 1 equals -56 for 0.1 minus 4. 4.1 minus 4 is 0.1. So y plus 1 equals -5.6. Then I can subtract 1 from each side and get y equals -6.6. Why is this a good approximation of the true value of the function? Well, because 4.1 is very close to 4. And when I use an x value close enough, then my tangent line is going to be very close to the value of my function. Our final page is a graphical analysis. Checking our graph, this is the graph of the derivative, graph of my derivative, of a polynomial function. P is continuous, differentiable, and I have 5 questions to answer. Our first question asks, on which intervals is the graph of the function decreasing? Justify your answer. So we're going to start with justifying the answer. How do I know where the function is decreasing? Well, my function decreases where what? The derivative is negative, which is on the interval. Now, where on this graph is my derivative negative? What's another way that I can say negative? I could say less than 0, but graphically, what does negative mean? Negative means below the x-axis. So my function is negative here and here. Now, it's important to note, what is my derivative's value right at 0? My derivative's value is 0. Is 0 negative? 0 is neither negative nor positive. So when I'm taking this interval, I can start at -3, but I need to stop at 0 and pick back up at 0 again. and then I can take that all the way to positive 3. So if this is where my function is decreasing, where is my function increasing? Where does p of x increase? And what's my justification? Well, p of x increases where what? Well, it increases where my derivative is greater than 0. And my derivative is greater than 0 on the interval. And what's another way graphically of saying greater than 0? Well, greater than 0 is above the x-axis. So where does this function begin to be above the x-axis on the left? Well, this is understood to just have an arrow, which means even though it's fairly slow, it is going infinitely to the left, and I'm going to start with negative infinity. And this ceases to be positive at negative 3. What other interval is the derivative positive and therefore the function increasing? My derivative continues to be positive at 3, resumes being positive at 3, and continues to be positive until positive infinity. Number 23 asks, at what values of x does the graph reach a relative maximum? Justify my answer. How do I justify a relative maximum? Well, my function has a relative maximum where? How do I know that I have a relative maximum? What are my two conditions? My first condition is that my derivative equals 0, or my derivative equals 0, and a maximum means my second condition is that my slope changes from positive to negative, or in other words, where my derivative changes from positive to negative. For this particular graph, it changes from positive above the x-axis to negative below the x-axis at x equals negative 3. Number 24 asks, where do I have a relative minimum on my function? My function has a relative minimum where what? How do I know that my function has a relative minimum? Firstly, because my derivative equals 0. And then secondly, my derivative must also change from. A relative minimum will look like this, meaning that I start with a negative derivative and then become a positive derivative. So my derivative will change from negative to positive. And on the graph, where does my derivative change from negative to positive? From below the x-axis to above the x-axis? It changes at 3. X equals 3. That is my where. Number 25 asks us to approximate the value of the function at 1.8 using tangent line approximation if p of 2 equals negative 3. So to do tangent line approximation, I need to get an equation of a tangent line. And to find the equation of a tangent line, what two pieces of information do I need? I need the point of tangency and the slope of tangency. What am I given as my point of tangency? My point of tangency is here, x equals 2, y equals negative 3. How do I find my slope of tangency? Well, the slope of my tangent will be my derivative at 2. So I need to find my derivative at 2, and looking up at my graph, this is a graph of the derivative. So I want to read the value of the derivative from this. At 2, my derivative's value is negative 4. So the slope of my tangent equals negative 4. Now I can find the equation of my tangent line, negative 4x minus 2, y plus 3 equals negative 4x minus 2. And I'm asked to approximate the value of 1.8. I'm going to use this form because that allows me to work with smaller numbers. So for my tangent line approximation, y plus 3 equals negative 4 times 1.8 minus 2. Now I can do that 1.8 minus 2 inside the parentheses, which will be negative 0.2. Y plus 3. Negative 4 times negative 0.2. 4 times 2 is 8, 1 decimal, positive 0.8. And I subtract 3 from each side and get negative 2.2. So this is my tangent line approximation of 1.8 if p of 2 equals negative 3. So y equals negative 2.2, and that is my approximation of the function of 1.8. And we've completed lesson 2.5.